Welcome back. Last time we briefly touched on Ludwig Prandtl, a true giant in the world of aerodynamics. Well, today we're going to dive deep into his theories, the incredibly elegant insights that finally cracked the code of flight and really laid the foundation for every modern aircraft you see in the sky.
To really get Prandtl's genius, you have to understand the wall he and everyone else was up against. You see, in the early 20th century, the mathematics of how air flows was monstrously complex. So much so that trying to predict the forces on something like a wing was practically impossible. So what do you do? What do you do when a problem just seems completely unsolvable?
You simplify it. And that, right there, that was the core of Prandtl's revolutionary insight. He realized you didn't have to solve the entire, messy, complicated problem all at once. His true genius was in finding a brilliant way to divide and conquer it.
So, here's our plan for today. We're going to start with Prandtl's big breakthrough idea and talk about why it was so desperately needed. Then, we'll see how it literally shapes the world around us, touch on the beautiful math behind it all, and then we'll set the stage for our next explainer where we get really practical.
All right, let's jump right in with Prandtl's single most important contribution, the idea that changed absolutely everything, his divide and conquer approach.
Back in 1904, Prandtl came up with what we now call the boundary layer theory. He basically said, hey, what if we stop trying to solve for everything everywhere? What if the air flowing around a wing can be split into two totally different regions? First, you've got this super thin layer right next to the wing's surface, the boundary layer. And in air, viscosity, the stickiness or friction of the air, is the only thing that matters. And second, there's the entire region outside that thin layer where we can just pretend the flow is perfect, completely frictionless. And this slide right here shows you that strategy perfectly. Inside that boundary layer, you have to deal with all the complex, sticky effects of friction. But outside of it, you get to use much simpler math for a perfect, frictionless fluid. By breaking the problem into these two zones, each part, for the first time ever, actually became solvable. It's brilliant.
So why was this idea so earth-shattering? I mean, it sounds kind of simple, right? Well, it's because before Prandtl, the best theories they had led to a conclusion that was just completely and honestly laughably wrong. It was called Dallin-Barrett's paradox, and what it said was that the math predicted an object moving through a fluid would experience zero drag. Yep, zero. Now, anyone who's ever stuck their hand out of a moving car window knows that is just impossible. This wasn't a small error, this was a massive, fundamental disconnect between theory and reality, and it was holding back the entire field of aviation.
Prandtl's boundary layer was the missing piece of the puzzle. It finally explained where drag actually comes from. It's the skin friction inside that tiny thin layer, and it's the pressure changes in the wake that forms behind the object because of that layer. All of a sudden, for the first time, theory lined up with the real world. Engineers could finally start to accurately predict and design for drag.
Okay, so how did this theory actually shape our world? Because Prandtl's ideas weren't just some dusty academic exercises. They became the absolute bedrock of modern engineering. I mean, the impact is just enormous. This whole approach was foundational for designing pretty much countless airplanes and ships all through the 20th century. It made it possible to reliably calculate lift and something called induced drag on real, finite wings. It also led directly to these powerful computer techniques called panel methods, which are still used today to model airflow over everything from Formula One cars to passenger jets. Heck, even architects use these same principles to figure out wind loads on skyscrapers.
Now let's take a quick peek at the math behind all this magic. See, Prandtl's real gift was his ability to translate his physical intuition into powerful and often beautifully simple mathematical tools that actual engineers could use to build things.
So, take his lifting line theory. A real 3D wing is incredibly complex to model. Prandtl's approach? He simplified the whole thing down to a single line of swirling air, what we call vortices. Now, it might sound a bit abstract, but this one simplification gave engineers a solvable model to predict lift and drag based on a wing's shape, especially its aspect ratio, which is just how long and skinny it is.
But you know how it is. Engineers always want to go faster. And as aircraft started approaching the speed of sound, a whole new problem popped up. Air stops behaving like it's incompressible. Its density starts to change, and that just messes up all the simple equations.
So what happens? Well, Prandtl, this time working with Hermann Glauert, developed another ingenious simplification, the Prandtl-Glauert rule. Honestly, the best way to think about it is as a kind of mathematical cheat code. It's a correction factor that lets an engineer take a simple answer they already have for low-speed flight and use it to predict the forces in much more complex, high-speed flight where the air is getting squished.
And here is the payoff. You can see it right here on this graph. It shows a wing's ability to generate lift as it gets faster and faster. See that? As the speed gets close to Mach 1, the speed of sound, the theory predicts this dramatic, incredibly sharp increase in lift. This was an absolutely critical insight for designing the very first aircraft that could break the sound barrier.
So, what's the big takeaway here? Prandtl gave us the fundamental toolkit. His brilliant, elegant simplifications made the impossible possible, and they allowed engineers to finally, truly understand and predict the complex forces of flight.
So, we've covered the what and the why behind Prandtl's key theories. He gave us the intellectual tools to design things that fly. In our next explainer, we're going to roll up our sleeves and actually apply these theories to see how an engineer would solve a real-world problem. Hope to see you then.